So again, our review problem. Power law fluid. I'm just gonna draw. I haven't rebooted my computer in 3 days, therefore I'm having my regular issues. So if my drawing is a little strange, that's because I'm drawing like this. So this is radius R, and then there is some fluid that goes up to R plus delta. And this is my z direction. So when I say derive, I do expect you to do a full derivation. Has anybody started shell balance?
It's necessary to start from the whole shell balance because then they derive the first order differential equation with velocity.
Yes.
Okay. From the beginning. Right.
I'll be more explicit. I want you actually to do the shell balance right now, just as a review.
Okay.
But I'll wait for you, because if I do it, you'll be just like, oh, yeah. So I will catch up with you. You'll just give me the equation to start from. How's that?
Okay.
In terms of phi, combined momentum. So I'll just go to... And this being power law fluid, so just a quick discussion. So yes, you can do shell balance and you will derive an equation to start from.
Start like this. Stay in the momentum equation. Stay equations, and we plus is incorrect. It would be incorrect in exam if I start.
In this particular case, actually, I did not say specifically shell balance, so it would be correct.
Oh, okay.
I want you as a review now to do shell balance. Now, just as a taken, the moment you see power law fluid, okay, or in general, what I would suggest is a good idea, is instead of using formulas that are directly expressing differential equation in terms of velocity, even though velocity, well, here you don't want to solve, so it doesn't really matter. But if you want to solve the problem, you're much more likely to solve if you just use the equations that actually have tau inside, the shear stresses. And then solve for shear stress first. And then solve for velocity. Because that way you're kind of going layer by layer in terms of differential equation, order by order, really, in terms of differential equation. So that's typically a better strategy. But if I were using a shell balance here, did anybody get to the differential equation for phi for the combined flux? Yes. What is it? Wow. Exam is tomorrow. Okay. 1 over R.
Yeah, 1 over R. Partial. ERC
with respect to r. Mm-hmm. Mm-hmm.
Plus.
All right. Okay. So this is my starting point. What is my assumption on velocity?
Only C velocity.
Only z velocity and dependence only on. Okay. And then the other two are 0. Okay. Now here we kind of have this gravity effects, but other than that, I don't have any pressure, right? So this is because it's kind of acting all around, so it's canceled out. So dp dz is 0. Okay. Okay. So my phi z, is pressure plus tau zz plus rho vz squared. Okay. And my phi rz is tau rz. Now, this tau zz term, involves partial derivative with respect to z. Therefore, it's going to disappear. So I really have.
You don't have pressure also.
And we don't have pressure. Well, dp dz is 0, so that's going to disappear once I do a derivative. But right now, it's pressure is there. Okay. So basically, I will have minus 1 over r ddr of r tau rz minus this, now dp dz disappears, plus rho g is equal to 0. Okay. So far, nothing that we haven't seen before, so I can go and do rho g r. Okay. And when I integrate r tau rz, and plus c1, and my tau rz is rho g r over 2 plus c1 over r. So now I need boundary conditions. What is my boundary condition for tau rz?
And R is 0.
Mm-hmm.
Other part plus delta is tau equals 0.
Shear stress is 0.
Okay, so shear stress at r plus delta, right, is contact with air. Okay, and because of that, we approximate it as a 0, assuming that there are no super high velocities involved here. And that gives me my C1 as minus rho g over 2 r plus delta squared. What do I know about the solid surface?
Velocity 0.
Hmm? Velocity is 0, but in terms of shear stress, all I know is that shear stress is maximized in its absolute value there. Okay, but I don't have it as a boundary condition for shear stress. Okay, so this is where I know my tau rz, and basically it has, I'm going to take a new page. So my tau rz is rho g, I'm going to write it as follows. R divided by, in some sort of normalized form, minus r plus delta over r. in thin films and in annulus, you will often have both sort of R term and 1 over R term. Now, what is the, if I'm thinking of tau RZ profile, if this is my R, this is my R plus delta. Okay. I know it's 0 at R plus delta. What is it for R? What is this? So I can plug it in. Is it positive or negative? Okay. So it's plug in, and this is a negative value. So what I have is sort of a 0 here. And then it's some negative value here. Okay. Uh-huh. And I need to figure things out for power law fluid. And this is why I'm actually looking at the sign. Because for power law fluid, my tau RZ is minus M dVz dr to the n minus 1 dVz dr. So M and N are given constants for power law fluid, and I know that this is negative, right? So what do I know then about dVz/dr? Positive. Absolute value is positive. This is negative here, therefore dVz/dr is positive. That means that I can remove the absolute value. Okay? So once you have shear stress, don't be afraid to look at it. Right? I have the equation. How does it look like? Right? Is it positive? Is it negative? Is it, and especially with power law fluid, you want to get rid of that absolute value in order to be able to proceed. Right. So then, basically, then I have that my tau RZ is, as a matter of fact, in this case, in this coordinate system, do note that, like, if you flip an axis in a coordinate system, you might get a different expression, and it might be positive, right? So it's really relative to that coordinate system. It's not a big deal. Okay? And that is equal to rho g r plus delta over 2 r over r plus delta minus r plus delta over r. So my dVz dr to the nth power is, I'm just going to write in silence here, so I reverse the order because I multiplied by minus, or divided by minus m, and therefore it is obvious why we're not going to solve this analytically. Well, maybe we can for n is equal to 1, but that's not power law. Not proper one anyway. So don't be afraid to look at the shear stresses. What are the values? Other than that, it's not a very difficult problem, but if you kind of get stuck there, then you're just kind of looking at it and you're like, oh my God, what is this? So try to get rid of the absolute value if you can. Okay? All right. So that's our review problem. You can look at the others at your own time, and I'm just going to continue with our friction factors. Okay. So where did we stop last time with friction factors?
Adding two velocities.
We arrived at two friction factor expressions. The way they're expressed is by looking at the pressure drop, okay, and its relationship to Darcy's velocity and porosity. And in laminar flow regime, this relationship is linear. This is something that we are familiar from Darcy's law. Okay, linear relationship between gradient of pressure and velocity. In turbulent flow, we actually have a quadratic relationship. Now we can actually notice that if I simply look at both of them at the same time, okay, question is, so this is for, and we have derived, or we have mentioned that Reynolds number for sphere packings is something slightly different from what we're used to in simple geometries. In particular, that Reynolds number has to have porosity within. Okay? It has Darcy's velocity, it has mu, it has a particle diameter as sort of some sort of dominant measure of the geometry and geometry widths. It's not very far off. I'm not flowing through the particle. I'm flowing around the particles, but when I actually put particles in a packing, the average cross section that I see that is controlling my flow is a fraction of this diameter. So it's typically 1/5 of it. Like that's a good guiding. If you have nothing else, that's a good guiding rule. It actually comes from mono-sized sphere packs. Okay? So dP is still a good, basically, measure of constricted pathways through this sphere pack. So this is my Reynolds number. So for very low Reynolds numbers, or less than 10, I have what we call Blake-Kozeny relationship. And for very large, I have Burke-Plummer. In between, if I just add them together, okay, I will notice that for very small velocities, this V0, the quadratic term will be even smaller, and therefore it will basically asymptotically disappear. And for very large velocities, it's the linear term that will disappear. So these two things actually work well together if I just put them together. And basically in some transient regime, well, I expect that it's just going to work in between. And that is actually indeed the case. So let's just put the equations together, and then I'm going to show you that it actually works. I think, this is the one. So basically for transition regime, I'm going to put that as a C. We will simply add A and B together. So my P0 minus PL over L is Blake-Kozeny This is quadratic term. And this is so-called Ergun equation. Let me quickly go back to my PowerPoint. Mm-hmm. It indeed works. Look at that. Dots are the data. Blake-Kozeny for smaller Reynolds numbers. Burke-Plummer for larger ones. And in between, woo, kind of following that trend just fine. So Ergun equation is actually the one. So let's just look at it a little more. So what is this connection between Blake-Kozeny and the Darcy's law that we saw before? So I'm gonna put this works. See figure 642 in BSL. So what is the connection between Blake-Kozeny versus Darcy's law? So I have that my P0 minus PL over L is 150 mu V0 over dP squared, 1 minus phi squared over phi cubed. And my Darcy's law says that V0 is minus K over mu gradient of pressure, and gradient of pressure is P0 minus PL over L. So if I write the blue equation in Darcy's law form and compare, I'm going to get that V0 is 1 over mu. Actually, nobody said anything. Right? Gradient goes larger minus smaller, but I have a minus, so these two things have correct signs. So I have 1 over mu dP square phi to the cube divided by 150 . So when I compare the two, my permeability comes to be this. And that is not fair. So if you remember, officially our permeability was dp squared phi cubed over 72 tau, where tau is tortuosity. No relationship to shear stress. So basically my 72 tau is 150, so tau is 2.08 or so, right? That's a reasonable value. We don't have a value for tau. It's a fitting parameter. What it's saying is, like, as I'm going through the porous medium, I'm going twice the length than I would go if I just went straight from one point to another. Okay? So we did say that 2.5, if you don't have anything, 2.5 is common for sphere packs, which would give you about 180. Again, those things are all relative, and ultimately you fit to the values you have. So it's fine. As good of a match as you will get subsurface anything. Okay. Now, when do we let's just take a little bit and poke around. When do we expect flow to actually be turbulent? If I'm in a sedimentary rock, no. Okay. You have micron-sized grains, probably less than 300 to 400 microns in cross section. You're not going to get. Darcy's law is valid inside of the rock itself. However, there are two places where you could actually transition to turbulent rock, and they're very common in petroleum engineering. That is once you actually open a fracture. And inside that fracture, if it's propped fracture, you have grains that are typically up to 10 times larger than that of a host rock. Okay. So this is where you could start transitioning in the regime. And you could also have just some sand production and larger pieces of grains chip off from the formation itself and fill that space as well. So basically, if I actually look at a little bit in terms of the values, so do we expect turbulent flow in rocks? So my mu is often data taken as that of water, 10 to the minus 3 Pascal second. If I look at the dp, that is 1 millimeter, so that's 10 to the minus 3 meters. Porosity of 0.4, and my rho is that of water, 10 to the 3. So just to give me numbers. Then my Blake-Plummer relationship is valid for dp rho v0 mu over minus v larger than 10 to the cube. So when I plugged in the values that I stated here that are kind of standard, then v0 would have to be larger than approximately 0.6 meter per second. 60 centimeters per second in a piece of rock with 1 millimeter grains, that's a bit pushing it. Anybody here in the lab, do you get those velocities ever? No, I hope not. Okay. Okay. So this is something that's unlikely in a rock, possible in fracture. I'm just going to say near wellbore, okay? Due to damage or propant. And of course, if you're going to estimate drawdown within a fracture, you do need better relationships than just Darcy's law. And then just one more comment. And I'm going to show actually pictures that are from the notes. So there is a book that most of you probably know, Dalian, that is on flow in porous media. It's a classic. Okay, now I need. Oh. No. Apparently now I can't find the notes. And I have them printed in my hand, but good luck finding. Now it's a guessing game to figure out which one. I'm gonna show it good old classical way.